Objectionable current is defined as current flow on ground electrode conductors that creates 15 volts or more to earth on light switch boxes. This voltage level indicates a potentially hazardous condition and compromises the effectiveness of the grounding system. Equipment grounding conductors should be connected directly to the ground electrode and not to the neutral bus. Connecting equipment grounds to the neutral bus can create a parallel path for neutral current, leading to objectionable current on the grounding system. This parallel path can result in elevated voltage on metallic parts of equipment and increase the risk of electric shock. Current flow that causes the soil around the ground rod to dry out is also considered objectionable current. Dry soil increases the resistance of the grounding system, reducing its ability to effectively dissipate fault current. This can lead to higher voltage levels on equipment and increase the risk of electrical hazards. The integrity of the grounding system is critical for safety and proper equipment operation. When objectionable current is present, it indicates a problem that needs to be addressed promptly. Identifying and mitigating objectionable current involves several steps. Firstly, check the voltage between the ground electrode conductor and earth at various points, such as light switch boxes and metallic enclosures. If the voltage exceeds 15 volts, further investigation is necessary. Secondly, verify that equipment grounding conductors are properly connected to the ground electrode and not to the neutral bus. Correct any improper connections to eliminate parallel paths for neutral current. Thirdly, inspect the soil around the ground rod for dryness. If the soil is dry, consider measures to improve its conductivity, such as adding water or using a ground-enhancing compound. The causes of objectionable current can vary. One common cause is improper wiring, such as a neutral-to-ground fault. This can occur when a neutral conductor accidentally comes into contact with a grounded metal enclosure. Another cause is unbalanced neutral currents due to uneven loading on different phases of the electrical system. This can result in neutral current flowing through the grounding system. Additionally, external sources of current, such as ground faults on neighboring systems, can contribute to objectionable current. To mitigate objectionable current, firstly, identify and correct any wiring errors or faults. This may involve tracing circuits and testing for continuity between neutral and ground conductors. Secondly, balance the load on different phases of the electrical system to minimize neutral current. This can be achieved by distributing loads evenly across phases and using power factor correction equipment. Thirdly, ensure that the grounding system is properly installed and maintained. This includes using appropriate size ground electrode conductors and ensuring that all connections are tight and corrosion-free. Fourthly, consider using isolation transformers to isolate sensitive equipment from the effects of objectionable current. Isolation transformers provide a separate ground reference for the isolated equipment, preventing current from flowing through the grounding system. Fifthly, implement a regular testing and maintenance program to monitor the performance of the grounding system and detect any signs of objectionable current. This should include periodic voltage measurements and visual inspections of the grounding system components. The National Electrical Code, also known as NEC, provides specific requirements for grounding and bonding to minimize the risk of objectionable current. NEC Section 250.6 addresses objectionable current and provides guidance on how to identify and mitigate it. NEC Section 250.24 specifies the requirements for grounding the neutral conductor at the service entrance. NEC Section 250.50 outlines the requirements for the grounding electrode system. NEC Section 250.96 requires bonding of metal enclosures and other non-current carrying metal parts to the grounding system. NEC Article 250 covers grounding and bonding in detail and should be consulted for specific requirements. Proper grounding and bonding are essential for electrical safety and equipment protection. By understanding the principles of objectionable current and following the requirements of the NEC, you can minimize the risk of electrical hazards and ensure the reliable operation of electrical systems. Maintaining a low-impedance ground path is crucial for clearing ground faults quickly and safely. A high-impedance ground path can limit the flow of fault current, delaying the operation of overcurrent protective devices and increasing the risk of electrical shock or fire. Therefore, it is important to use appropriate size ground conductors and ensure that all connections are tight and corrosion-free. Regular inspections and testing of the grounding system are essential to verify its integrity and effectiveness. This includes visual inspections of ground connections, testing for continuity between ground conductors, and measuring ground impedance. Any deficiencies or problems should be addressed promptly to maintain the safety and reliability of the electrical system. The use of ground fault circuit interrupters, also called GFCIs, can provide additional protection against electrical shock. GFCIs are designed to detect small imbalances in current flow and quickly interrupt the circuit, preventing electric shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where the risk of electric shock is higher. In addition to grounding and bonding, surge protection is also important for protecting sensitive electronic equipment from voltage surges. Voltage surges can damage or destroy electronic equipment, leading to costly repairs or replacements. Surge protective devices, also called SPD, are designed to divert surge current away from sensitive equipment, protecting it from damage. SPD should be installed at the service entrance and at branch circuits that serve sensitive electronic equipment. Proper grounding and bonding are essential for the effective operation of SPD. The grounding system provides a low impedance path for surge current to flow to ground, protecting equipment from voltage surges. Therefore, it is important to ensure that the grounding system is properly installed and maintained. Understanding the principles of grounding and bonding is essential for anyone who works with electrical systems. This includes electricians, engineers, and maintenance personnel. Proper grounding and bonding are critical for electrical safety and equipment protection. By following the requirements of the NEC and implementing best practices, you can minimize the risk of electrical hazards and ensure the reliable operation of electrical systems. Improper grounding can lead to a variety of problems, including electrical shock, fire, and equipment damage. Therefore, it is important to take grounding seriously and ensure that it is done correctly. If you are not familiar with grounding principles and practices, it is best to consult with a qualified electrician or engineer. They can help you design and install a grounding system that meets the requirements of the NEC and provides adequate protection for your electrical system. Remember that electrical safety is everyone's responsibility. By understanding the principles of grounding and bonding and following safe work practices, you can help prevent electrical accidents and ensure a safe working environment. Current flow on ground electrode conductors is typically caused by a few factors. Firstly, ground faults within equipment can cause current to flow to ground. Secondly, neutral current can find its way onto the grounding system if there are improper connections between the neutral and ground conductors. Thirdly, external sources of current, such as nearby electrical systems, can induce current flow on the grounding system. The effects of current flow on ground electrode conductors can be detrimental. Firstly, it can create objectionable voltage on metallic parts of equipment, increasing the risk of electric shock. Secondly, it can cause the soil around the ground rod to dry out, reducing the effectiveness of the grounding system. Thirdly, it can interfere with the operation of sensitive electronic equipment. There are several methods to mitigate current flow on ground electrode conductors. Firstly, identify and correct any ground faults within equipment. Secondly, ensure that the neutral and ground conductors are properly separated and connected. Thirdly, use isolation transformers to isolate sensitive equipment from the effects of current flow on the grounding system. Fourthly, implement a regular testing and maintenance program to monitor the performance of the grounding system. The ground electrode system is a critical component of the electrical system. It provides a low impedance path for fault current to flow to ground, protecting people and equipment from electrical shock. The ground electrode system typically consists of one or more ground rods, ground plates, or metal water pipes that are connected to the grounding system. The ground electrode system should be installed in accordance with the requirements of the NEC. The ground electrode system should be tested periodically to verify its effectiveness. The testing should be performed by a qualified electrician or engineer. The results of the testing should be documented and maintained for future reference. The grounding system should be inspected regularly for any signs of damage or corrosion. Any damaged or corroded component should be replaced promptly. The grounding system should be maintained in good working order to ensure its effectiveness. The size of the ground electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the ground electrode conductor based on the size of the service entrance conductors. The ground electrode conductor should be made of copper or other approved material. The ground electrode conductor should be protected from physical damage. The ground electrode conductor should be connected to the ground electrode using approved connectors. The connection should be tight and corrosion-free. The ground electrode conductor should be installed in a manner that minimizes the risk of damage. The ground electrode conductor should be routed in a straight line whenever possible. The ground electrode conductor should be supported at regular intervals. The ground electrode conductor should be protected from contact with other metal objects. The installation of the grounding system should be performed by a qualified electrician or engineer. The electrician or engineer should be familiar with the requirements of the NEC and should follow all applicable safety procedures. The installation should be inspected by a qualified inspector to ensure that it meets the requirements of the NEC. The inspection should be performed before the grounding system is put into service. The inspector should verify that all components of the grounding system are properly installed and connected. The inspector should also verify that the grounding system is effective in providing a low impedance path for fault current to flow to ground. The importance of proper grounding cannot be overstated. Proper grounding is essential for electrical safety and equipment protection. By following the requirements of the NEC and implementing best practices, you can minimize the risk of electrical hazards and ensure the reliable operation of electrical systems.